Welcome, everybody. Good afternoon. I'm David DiBiase with ARP Virginia. I'm an Associate State Director, and I'm here to give you a brief welcome. We're thrilled to be working with the Osher Lifelong Learning Institute at George Mason University. Our founder, Ethel Percy Andrus of ARP, has been a champion of lifelong learning. I'll read you a short quote from her. "The eagerness to learn, to pioneer in the development of new skills and new abilities, to broaden the personal scopes of understanding, to freshen the mind with new ideas and new concepts, to achieve new heights of knowledge. The eagerness to learn has no age restrictions." Studies have shown that our brain is stimulated when we learn new things, makes new neural connections when we pursue new interests. And ARP encourages you to stay curious, give your mind a good mental workout, do things that you enjoy, and grapple with ideas that really make your mind, make your mind grapple with complexity. It's important to note that it's never too late to seek out a new cognitively stimulating activity. So with that, we say thank you for joining us. I want to turn it over to the Executive Director of OLI Mason, Jennifer DeSano, to tell you a little bit more about their program and introduce you to the guest speaker. Jennifer, the screen is yours.
Thank you so much, David. And thank you to AARP for this collaboration. The Osher Lifelong Learning Institute at George Mason University has been in existence now for 30 years. And we serve all kinds of wonderful individuals who participate in joining us in classes and as teachers and as volunteers. There are many things you can learn and do at the Osher Lifelong Learning Institute at George Mason University. I want to welcome all of our members who are on the call, as well as those of you who are in Northern Virginia and across the United States joining us through the AARP connection. You can learn more about OLLI at olli.gmu.edu, and we'll put that in the chat. And we are very happy to be collaborating to bring our wonderful speaker here today. His name is David Draper. He is NASA's Deputy Chief Scientist and is an Earth and planetary scientist with 28 years of professional experience in studying the Earth, Moon, planets, and solar system. His prior experience includes leading the Astromaterials Research Office at NASA Johnson Space Center in Houston, Texas. Please give a warm welcome to David Draper. Thank you.
Well, thanks very much, Jennifer. And it's a great pleasure to be here today talking with you. I only wish that we could be together in person. I love coming to talk to folks about what we're doing at NASA. I first always like to start these kinds of conversations with a thank you to all of you out there all of you taxpayers, basically, who pay our salary and support us in what we do. NASA has a long-standing history of bipartisan support in the Congress and through multiple presidential administrations of both parties, and strong support from the citizens of the United States. And we never want to miss a chance to express our thanks for that support. And so, Meg, if you want to go ahead and pull up the presentation, I'm going to take just a couple minutes before I dive into the content, kind of tell you how I got here, how I got to be where I am. Typically, when I have audiences like this, that's always a question I get. How do you get to do what you're doing? And so I know it's going to take Meg a second or two to put the full screen thing up. So let me just start with that. Now, I was born in 1960. And so I'm one of the Apollo generation. I grew up during the years when NASA's mission to the moon was mandated by President Kennedy in the early 1960s, before this decade is out and all of that. And although I'm a little too young to remember the Mercury program and most of the Gemini program, by the time the end of Gemini and the beginning of Apollo was going, I was pretty tuned in, and I grew up eating, drinking, breathing the space program. Never in my wildest dreams did I think I would ever get to be part of it. Later on, as I got a little older, my interest changed, and I decided I wanted to be a musician. And so I studied classical guitar for most of my youth. Got into the obligatory garage bands during high school years and all those good things. And By the time I was getting to be 20, 21 years old, though, I had a kind of an epiphany and realized that I was probably never going to make it as a musician. You have to be really good, for one thing, and it takes a lot of luck. It's a hard life. At the same time, I was taking a geology course to kind of check a box as an arts major for doing some kind of lab science. And that was the year that Mount St. Helens blew up in the state of Washington. That's perfect, right where you are, Meg. We can just leave it right there. And that changed my life. I had been taking this geology course, really fascinated by learning how the world works. And when that happened, it was just a game changer for my mindset. And so I decided to make a 180-degree change in my life plan, got into science, technology, got a degree in geology at Humboldt State University in Northern California, went on to the University of Oregon in Eugene, Oregon to get my PhD. My area of emphasis is on how volcanoes work on the inside, deep under the ground where the processes start to give rise to volcanoes. Now, as it turns out, those processes are just the same kinds of things that happen on the moon and on Mars and on Venus and Mercury and other planets in our solar system that are made of rocks, in comparison to the ones in the outer solar system, which are the big gas giants. I'm not going to be talking much about them today. So the background that I had in geology actually was really, really applicable to trying to study other worlds. And through my whole career is nothing but a unending series of lucky breaks of being in the right place at the right time. And I was able to take my geological knowledge and I had the chance to get involved doing planetary science by coming to NASA Johnson Space Center, just at first as someone who ran a laboratory, but then I worked my way through and up and got, proved myself to be of some value. And I got to join NASA as a real government employee about 12 years ago or so at NASA Johnson. And the group we led there, we studies the samples of other worlds. You heard Jennifer in her introduction talk about the Astromaterials Research Office. Astromaterials is the fancy word we give to any piece of stuff that comes from someplace besides Earth. So we have the lunar samples from Apollo, we have meteorites, we have cosmic dust, we have samples of comets' tails that have been retrieved by spacecraft, we have atoms and molecules of the solar wind that have been returned by spacecraft. We study these things so that we can understand how the solar system works, how it came to be the way it is now from the original ball of gas and dust some 4.7 billion years ago or so. And basically what we have been able to do is put together the jigsaw puzzle of the story of our solar system from just a few pieces and a really fuzzy picture on the box top. And it's been a challenge, and it's an ongoing challenge, but it is incredibly rewarding. And I hope that by the time I get done today, you'll share a bit in some of the wonder and frankly awe that comes out of the study of other worlds. So what I'm going to do for you today, here's the outline on your screen. I'm going to go through 4 sections. I'm going to start with the latest from our most recent mission to the surface of Mars. That's Mars Perseverance. I'm going to spend the first half of my time basically talking about the latest from that. We're going to look at the landing videos and some really cool photographs. And then, because I know, that's the latest and greatest stuff. I know people want to hear about that. And then the second half, I'm going to talk about our agency's plans for returning to the moon. But before I do that, in section 2, I'm going to try to set the stage a little bit by recounting very briefly the history of lunar exploration, where we went, what we learned. And then from that, in the third section, I'm going to talk about how we have come to know things about our own Earth that we could have only learned by going to the moon. And that has to do with just how our Earth-Moon system came to be. And then finally, in the last talk, I'll bring us home by focusing on our plans in the Artemis program to return to the moon to learn our way around living and working on another world's surface, so that we can ultimately go on to other planets, especially the red planet Mars. So next, please, Meg. All right, thank you very much. Okay, so here we are. First, here are the Perseverance section. This is the latest in a series of missions that NASA and our international spacefaring nation partners have been undertaking for quite some time. The first mission to Mars was one of the Mariner spacecraft in the late 1960s and into the early 1970s. The first spacecraft to actually orbit Mars was in 1971. In the mid 1970s, we had Viking 1 and 2, the first two major landers, really very capable spacecraft. Now, those were static landers. They landed someplace and just did their work where they landed. And then there was a big gap, and that's only because NASA was really focused on the space shuttle program and designing and developing what became the International Space Station during those years. But during the 1990s, things got going again with Mars Pathfinder and Global Surveyor toward the later part of the decade. And then in the 2000s, things really started to crank up. And we've had a constant series of missions going back to the Red Planet, both from NASA and from other agencies like the European Space Agency and the Russian Space Agency, Roscosmos. And so in the 2010s, there again, we have a pretty good fleet of spacecraft at Mars right now, and culminating in the most recent Mars Perseverance that just landed not too long ago. Next, please. Now, what I'm going to show you here is I'm going to start with some context of the part of Mars that we're landing on. Try to give you the big picture, as then we're going to zoom in and get a little more detailed. The main goal of the Perseverance mission is to try to establish whether the landing area was ever habitable, and what we mean by that was it capable at some time of supporting life? And the way the primary way to do that, in addition to they have instruments actually, bolted onto the spacecraft. This is a rover, like we've been sending for a while now. It is also the first step in a campaign to actually return samples from Mars. And this is a really critical thing to understand. There is absolutely no better way to understand how another world works than to have samples of that stuff in your hand that you know where it came from. Okay, now we also have meteorites from Mars, but we don't know where on the Martian surface they came from. They literally fell from the sky here on Earth, and we picked them up and found them, and we've learned how to determine that they're from Mars. We can talk about that in the Q&A. But now with Mars sample return, we will be able to pick them up from a known location and bring them back. Why is that so important? That's about geologic context. With the samples from Apollo, which we'll be talking about in the next section of the talk, we've had human beings on the surface picking them up and writing down in a notebook where they got it and what it looked like and taking photos and all the rest. So we have really good geologic context. That context is important because it tells us, you can pick up a rock at random and measure some things about it, its composition, its age, other things, but you don't know what the story is that you're plugging that into. Okay, so that context is just absolutely critical. So we'll be talking about that a fair amount as we go along here. And then the third thing that is happening on Mars Perseverance is the Ingenuity helicopter technology demonstration. You may have seen the news that Ingenuity, and of course, here at NASA, we're very fond of nicknames. So we refer to Perseverance as Percy, and we refer to Ingenuity as Jenny. And Jenny took her first flight just a couple days ago, and we're going to have a look at that. Now, I want to make sure this is real clear as well. A technology demonstration is just that. It is just demonstrating that something can or cannot work, and it's a high-risk thing. It's a roll of dice to see if it's going to work. There's no science instruments on board the copter drone. We're just kind of stretching our legs, stretching our wings, if you like, figuring out how this all works. And the things we learn from this technology demonstration, whether it would have worked or not, would have given us really good information that we can use to take those next steps. Okay, next, please. Now we're going to see the same two images on the right. Here's where we're going to start zooming in. What you see on the upper one is a little red circle and a yellow diamond there. That's the landing site where Perseverance ended up, and we're going to zoom in on that. Now, before we do, I want to explain the colors on these two diagrams, these psychedelic colors. These are used to denote topographic elevation. So the hot colors in the orange and the reds, those are high standing places, and the cool colors, the blues and the purples, are the low standing areas. So a couple things jump out when you look at Mars in this way. You see there's a real dichotomy, a real difference between the southern hemisphere and the northern hemisphere. In the view you're looking at on the upper of these two diagrams, the south pole of Mars is down. It's at the bottom. It's not at the very bottom. The globe is kind of tilted away into the screen a little bit, so the south pole is kind of pointing towards us from the bottom of that image. And so you're looking at a good view of the southern hemisphere. In contrast, on the bottom image, you're looking at mostly the northern hemisphere, and you see not only is it much lower in the blue colors, but as we'll see when we zoom in a little bit more, it's also much, much smoother than the really heavily cratered, high-standing southern hemisphere. All right, next, let's go ahead and zoom in. And okay, now this is a map of Mars. This is in real colors now. That has been unwrapped from the globe and mashed onto a flat screen. And it shows where NASA's Mars landers have ended up. Perseverance is there on the right-hand side. And we're going to be zooming in now one more time, please, Meg. And now, okay, we're looking at a globe picture again with normal colors. And what you see here is a white circle on the left-hand diagram of the main globe that's labeled Isidis Planitia. Planitia is just a basin or a plain. And so Isidis is a big basin, and the region we're going to is on one margin of this big basin. Now you look at the inset to the right-hand side of your screen, and what you're looking at is one edge of that Isidis basin. There you go. Yeah, Meg is pointing at it. Thank you. And then on that one, a little white circle that labels the little crater. You can just start to see the little circular shape of it, a crater that we have named Jezero. Next, please. Okay, here we are back to the psychedelic colors. Zooming in, you can see the low-lying, fairly smooth floor of Isidis Basin in the center of this image. Up to the left, now you can see the whole circle of Jezero crater that's being pointed to. And now we're going to zoom in one more time, please, Meg. All right, now what you're looking at is the edge of Jezero crater. So before we were looking at an edge that looks something like this, kind of an arc crescent shape, but we were zoomed way back. Now we've come way in and we're looking just at the edge of that little crater that we had in the circle in the previous thing. And the ellipse, the white ellipse on this diagram is labeled, this is the target zone that Perseverance was going to land in somewhere. We didn't know exactly where. Here's a new thing that Perseverance did that none of the other landers have done before. And bear with me, just take a little bit of explanation. We employed a technology that we call terrain relative navigation, TRN, because here at NASA we love to use acronyms, TRN, terrain relative navigation. What that is there are images and maps loaded on board the computers of the lander as it's coming in. And it has cameras taking snapshots of the ground many times a second as it's flying in, and comparing it to the images and the maps it has on board and saying, aha, I now know where I am. Exactly, because we have very good imagery of this area, of a lot of the Martian surface. And at a certain stage of the landing sequence, everything is hands off. The spacecraft itself takes over navigation, flies itself down to a place that looks safe using the algorithms and the images that are built in to the computer. Pretty cool. Next, please. Okay, on that diagram, you could just see the outlines of this pretty spectacular looking feature that we have chosen to go explore. And it is this funny looking bird's foot like sequence of stuff here right in the middle of this image. Now, this image also has false colors on it. They mean a completely different thing than before. I'm not going to, they're about what minerals are present. I'm not going to talk about that right now, but you can see the shape of this thing, and it looks for all the world like something we might see in a river delta here on Earth. Next, please. And sure enough, when we look at these things, this is exactly the kind of setting we're looking at. Anyone who's ever been to tidewater areas or the mouth of the Mississippi River or other places around the world where there are these large deltas, you can see there are river channels that just shift back and forth over time. If you've ever gone to a bayou, you can take a flatboat down one of these things one day and come back in a couple of weeks and that waterway is gone. It's not where it used to be. It's moved someplace. So this happens over a long period of time, and it lays down these sediments that are very distinctive to a geologist. A geologist who goes out in the field and sees this kind of rock can immediately identify, oh, that's a delta sequence. And that seems to be what we're landing next to on the surface of Mars. Next, please. Now, so this is what we think it might have looked like a long time ago. There's Jezero crater in the middle. Of course, this is an artist's conception. And we think that the whole crater was filled with water at some point. and that the river, that now the the landing site delta is in the upper left of the circle of the crater picture you're looking at. And water is coming in from that upper left. And, after it sits in the lake for a while, it ends up spilling out the other side on the right-hand side of this picture. And so the way a delta forms is when a river is coming down slope and it's carrying sediment in it because it has a lot of energy as it comes downhill. But then when it hits a standing body of water, there's just nowhere near as much energy to keep that sediment suspended. And all that load just drops out. And that's what forms the delta. Okay, so that's the kind of setting we think that we are exploring. And as a consequence of that, if that's true, if it is that kind of setting, the odds are about as good as they can get on Mars for finding the evidence. If there was past life on Mars, this is about as good a place to look for it as any on the entire planet. Next, please. Okay, this is a place we're now going to look at the landing video. This was Meg's going to click on it here, and we're just going to watch. It's about 3.5 minutes long, and it's got narration, so I won't be talking much. But we have cameras on board the actual lander taking video. It never happened before, so let's watch. So the thing is going to start right about a minute before the spacecraft's going to take over and fly by itself. It's in the what we call 7 minutes of terror phase, coming in and getting ready to land. Okay, well, I did drop the link in the chat to that. You may have seen this already, but basically it just showed the spacecraft coming down from its onboard cameras. I really encourage you to watch this later because it's like nothing you've ever seen before. And of course, everyone went nuts when everything landed properly. The President of the United States was checking it out from the White House. He called the acting administrator, Steve Jurczyk, a little while later to congratulate him and the team on their accomplishment. He ended up calling the entire team on the phone in a group call about a week later to talk to him for about 30 minutes. It was really good to see the White House taking an interest. Okay, next, please. All right, now here's another amazing photograph. Let me give you the context here. Now, what you're looking at in the main image, this is an image that is shot from one of our orbiters that's still there at Mars Reconnaissance Orbiter, in fact. And on the left-hand side of the diagram, you can see that delta, that chicken foot-looking deposit that there you go, thank you. She's waving the arrow around there. That's the thing we've been focusing on, the delta deposit. And then what you see, in the little white box, a little tiny dot. And when we blow up on that thing, we see that the orbiter caught a photograph of the rover floating down to the surface. You can see the parachute above and the rover itself below, floating on down to land before the jettison of the parachute, before it took over on its own power. Talk about a hole-in-one camera shot. You can't beat that. Next, please. There we go. And here we have a straight down shot taken with another one of our cameras, a high-res camera here. You can see that big delta feature now on the left, dominating the upper left side of the photograph. The yellow star in the center is the landing site, the final spot where the terrain relative navigation decided to land the rover. And the landing site was named after the great Hugo Nebula Award-winning science fiction writer Octavia E. Butler. And so it's the Octavia E. Butler landing. Next, please. All right, this is one of the first photographs taken from the rover. You can see it's highly distorted from it's kind of like what you do with your cell phone when you take a panorama. And you can see in the center of the image the dust having been scoured away from the landing spot by the rocket motors that were slowly lowering the rover to the ground during the descent and landing process. Next, please. We're gonna go lickety split through a few photos here. Now, here is one of the first outcrops that the rover took a photograph of, and I want to point something out. If you look in the far distance, you might at first think, oh, that's just the Martian sky, the kind of red sky. It's not. It's the rim of Jezero Crater. It's the wall of that huge delta deposit that I've been showing you in these images. In the foreground is just a little hummock of layered material, a little piece of that stuff that has then been eroded away from part of it, so you can see a cross section through those layers. So this just looking at this tells us a geologic story right away, that this had to be laid down. Something else happened later to partially erode it so that we can see it. So there's a couple episodes of the geologic history that we can get just from our first look. And then those rocks you see laying around in the foreground, we're going to have a close look at one of those in just a second. So next, please. All right, so this is taken from the underside of the rover now. There's a camera on the underbelly, and it took a photograph here of this is the business end of the rover. This is our robotic arm that has all kinds of instruments and gadgets on it to help us measure things. And what you can see there just to the left of that giant robotic arm is one of those rocks. So next, please. And, while they were checking out their instruments and getting, flexing their muscles and getting ready to roll, they say, here's a rock right next to us. Let's look at it. And this is the first thing we looked at. This turns out to be a basalt, a piece of lava. Jezero crater is next to a very large volcanic province, and the river that feeds the delta of Jezero cuts right through that big basaltic area. So it's no surprise that you would get a rock like this delivered by the river down to this basin. And I don't think you can see it. So next one time, Neg, please. This is going to show a little zoom in there. In that red box, you can just see a little row of dots. You can probably see that in the inset now. Those little dots are made by one of the instruments on that robotic arm. We call it SuperCam. And what it does, this is right out of science fiction, folks. What it does is it shoots a tiny laser beam at the rock from a distance, from however far away the thing is. In this case, it's about 10 meters away. And that laser beam, it shoots about, I want to say about 20 times a second, and it just hits a spot. And while that's happening, there is a spectrometer looking down the laser beam, and every time that beam hits the rock, it generates a little tiny puff of plasma. It just vaporizes a little bit of the rock, and it just keeps doing that. And the spectrometer can look at that cloud of vapor, of plasma, basically, and measure what it's made of. So it's a way for, and it's not a perfectly precise measure, but it's really good. And in the geology world, it's really good. It tells us a lot. And so what this allows us to do is, from any given spot the rover is sitting, we can look around, and instead of driving all the way over there and sticking an instrument up next to it and taking a measurement, we can do a couple of shots from the laser from a distance and get a first look and go, oh, okay, that looks a lot like these other things we've seen. Or, hey, this looks really different from everything we've seen. We better go take a closer look. So it's a really time-saving technique, but not just time-saving. It also gives us some really good kind of compositional information. Now, I know there's going to be a question: what sound does the laser make when it's shooting a rock on Mars? Because I think everyone wants it to be kind of like pew, pew, pew. I had to burst your bubble on that. You ever been to a restaurant? Remember restaurants? We used to go to restaurants. You would go to some place and it would have one of those things up on the wall to zap flies. It would be like an ultraviolet light with an electrified screen. If it was a fly buzzing, it would come and hit that thing and it would go zzz. That's what it sounds like. And it sounds like that, several times a second. So it sounds like zzz, zzz, zzz. These are the things only NASA can tell you. You want to know what something sounds like on Mars, you talk to us. Next, please. Okay, here we go. Now we're going to start talking about where are we going. Now, again, here is another image of our lovely Delta deposit. This is a traverse that is just sort of our game plan before we landed. This was drawn before we ever got to Mars. It's funny, as Meg and I were getting set up, we used the old expression, no plan survives first contact, with the enemy. And same thing's going to happen here. They're going to tweak and adjust this path as we learn things as we go along. But the basic idea is to go along the margin of the delta and then start to drive up into it and around up ultimately into the river channel that feeds this thing, and go into the source rocks that came down and formed the delta. This is going to take years to do. Perseverance, like Curiosity before it, is a nuclear-powered rover, and so it's going to have a pretty much limitless power supply. So it'll be able to operate for a good long time. If Lord willing and the creek don't rise. Next, please. All right, we're going to talk about the helicopter now a little bit. Meg, you might want to start thinking about that other link or not. I'll drop it in the chat as well. In fact, let me do that right now while I'm thinking about it while I talk. What we're going to see now in the next few images is the process by which the helicopter was unlimbered from the rover. Here, real quick, let me type in the Jenny flight vid link right there. Okay, and then next, please. So that's the housing that got dropped off. You can see the drone folded up on the underside. Okay, Meg, just go ahead and hit next every 15 seconds for the next like 5 things. So here it is, unloading, stretching its legs out, lowering to the surface, and now it's going to be sitting there ready to go. One more, please. Okay, let's stop there for a second. So Ingenuity, you can see that it's pretty small. It's that thing on top is its solar power pack. The Ingenuity rover is not nuclear powered. It is solar powered. It weighs only about 4 pounds. The first test was for it to see whether it could survive the Martian night and daytime. On Mars, at this photograph right here, it was taken very close to high noon on Mars. In the middle of the day, in near equatorial latitudes on Mars, the temperature gets to be kind of like what it is outside in Northern Virginia right now, high 50s. It's maybe at the most, it's usually a little cooler than that, but it's you would not too terrible. At night, however, completely different story. It gets a couple hundred degrees below zero. So anything that's going to work on the Martian surface has to be able to endure those big temperature swings. So as we saw, the first flight was just the day before yesterday. It launched and it hovered for 30 seconds. It kind of moved back and forth a little bit, and then it came right back down and stuck the landing. So we're Meg, if you wouldn't mind giving another shot to the YouTube thing. Oh, I'm sorry. This is the image that was taken from the copter looking straight down at its own shadow on the Martian surface. And that photo, they launched that thing at just about exactly high noon. So if we'll go ahead and give it the old college try, Meg, on trying to do the video. If it doesn't work, let's just go on. I put the link in the chat for people to look at. It's only a minute long. So if we miss it here while we're talking together, it's not a disaster. Some really great questions I can see in the chat. Looking forward to talking those. Hey, we got it. Okay, so you can see the copter. This is no sound here. The copter's in the middle on the bottom of the image. Its rotors are starting to spin, and here we go. And in just a moment here, you'll see it go popping off the ground. Whoop! There we go. And it went straight up, and a bit of a breeze hit it, and you'll see it kind of waft from one side to the other. You'll see it rotate. Well, it's just checking out all of its maneuvering capability. Kind of floats around a little bit. They said, all right, we did it, and back onto the surface. Now, all of this was done completely autonomously. It was all programmed into the drone ahead of time. There was no communication between Earth and the drone. There was no communication between the drone and the rover. This was all standalone kind of operations. Thank you very much, Meg. That's great. We can go ahead and go on now. Excellent. Perfect. Look at that. All right, next, please. Okay, and I just put this photo in because I wasn't sure I was going to
colon cancer. Because when caught in early stages, it's more treatable. I'm Cologuard.
We're hearing
a non-invasive
a TV commercial
in your stool to find 92% of colon cancers, even in early stages.
There we go. All right, thanks. I put this picture in just because I wasn't sure there was going to be video before today. So this is just a still grab from that video. We can go on. Thanks. All right, keep going, because that was the link we were going to go to. Okay, great. So that's our snapshot of our Mars Perseverance status as of this morning. The next flight of Jenny could be as soon as the day after tomorrow. We're going to do a few flights and kind of check that whole thing out. And then Percy is going to take off and start its serious science mission to go on for quite some time. And so there's going to be much more to come on this. And hopefully I'll come back at a time when we can all be together, and I'll give you another update. All right, let's go ahead and move on and talk about our lunar exploration plans. This is a video. Go ahead, Meg, while I talk. This is the early history of lunar exploration. It started in the 50s, and you'll just see this thing move to the right a bunch of, I'm not going to talk about all these different missions. These were all done in the space race era. The United States and the former Soviet Union, vying for supremacy and all those geopolitical things. But by the time it was all said and done, we had 6 Apollo human landed missions. And then later on, after Apollo, the Soviet Union flew a number of robotic missions called Luna. I named my dog Luna, by the way. And those were also sample return missions. They landed some rovers on the moon and brought back a small amount of sample that from locations that Apollo did not visit, and that was a scientifically very valuable thing to do. Next, please. Now, this all happened up until the mid-70s. Now, one more time, there we go, perfect. So here we are on the moon. This is from the Apollo 17 mission, the last of the Apollo missions, and that's Jack Schmitt, the LEM pilot from 17. He is the only trained geologist ever to fly to the moon, the only person in my field, the only scientist to ever live and work on another planet for a number of days. I've had the good fortune to get to know Jack really well, and I'll tell you what, he is still just as active as he ever was as a geologist and a planetary scientist. He comes to all the meetings. He stands up and asks questions. He gives talks. He's very engaged, and he is doing a wonderful job of helping to transfer his knowledge to the next generations to benefit from what he has learned. Next, please. And not just him. So here are the 6 places we landed on the lunar surface. Notice they're all on the near side, the side we can see all the time. They're all kind of near the equator as well, and that was largely for engineering safety. It's harder to land near the poles than it is to land near the equator for a variety of, frankly, rocket science kinds of reasons. We're going to talk about the lunar poles, though, at some length here in a little bit, so sneak preview. Next, please. Now, I'm going to take a couple of minutes here and talk about the samples that we brought back from the moon, because you remember me saying at the very beginning, there's no better way to understand another world than to have actual pieces of it taken in geologic context, and we have that with the moon. We have several hundred pounds of lunar samples brought back on the 6 missions. Each one of them, we know exactly where they came from, exactly what the environment was that they were collected from. And we learned some things we didn't know before. We learned that the moon is an ancient body. It's at least 4.6 billion years old. We learned that the early moon was once what we call a magma ocean. We're going to see this in animation here in just a minute. That was initially a ball of molten rock. We also found, we surmise from this that the way the Earth and Moon came to be was from a cataclysmic giant impact in the early history of the solar system. We're going to see some animations of that process here in a minute as well. We found out that impact cratering is a really important process in the solar system for shaping the surfaces. And we learned about the overall geologic history of when there was heavy bombardment, when there was volcanism, and when most of the geologic processes of the moon basically switched off, which was a little bit less than 3 billion years ago. Next, please. Okay, this is another one just like the first one. Go ahead and hit it, Meg. And this is the later generation of lunar exploration. Almost all orbiters starting in the 90s and into the 2000s from a number of countries, from the United States, from Japan, from the European Space Agency, from India, and from the People's Republic of China. This diagram's a little bit out of date now, unfortunately. The People's Republic of China have landed not 1 but 2 spacecraft on the lunar surface. They landed Chang'e 3 and Chang'e 4. Chang'e 4 landed late last summer in the early fall timeframe, and it returned samples of the moon to Earth for the first time since 1976, since the last Soviet Union Luna mission. That is a tremendous achievement. It is not easy to do robotic sample return from the moon. This is something that I've spent a lot of time thinking about myself and leading a team to try to propose a mission very much like the one that the Chinese did. So I know this material in detail. Very, very tough accomplishment, and they are to be congratulated. Next, please. Okay, I'm going to talk a little bit about now what we have learned now from having gone there. Here is a picture of the lunar near side on the left, far side on the right. As you probably know, we always see the same side of the moon when we look up at it. We always see the near side. It's what we call tidally locked to the moon. So it goes around the moon in the exact same time it takes to spin one time on its axis. So Earth takes 24 hours to spin on its axis. The moon takes 28 days, the same amount of time it takes to go around one time. And so we always see that same face. Of course, the all of the moon gets lit up at some point. There is no dark side of the moon. I'm sorry, Pink Floyd, but there is no dark side. It all gets lit up and it all gets dark at some point. But there are a couple of special regions on the moon that we're going to talk about that go outside those boundaries. Next, please. Now, this is another diagram like the one we saw about Mars earlier. This is topography again. So hot colors are high standing, blue colors, cool colors are low standing. And you see again, similar to Mars, there's a real dichotomy between the near side and the far side. The far side has a lot more high standing material, and the crust is much thicker on that side as well. It also has the biggest basin in the solar system on the far side. You see that giant purple splotch on the right-hand diagram. That's called the South Pole Aitken Basin. It is a huge feature that we think is also the earliest giant impact on the moon. We're going to talk a little bit more about that in a minute. Next, please. Oh, sorry, I just wanted to outline that. Okay, and we have now, in the years since we have been to the moon, we have now done some of the kind of work that we've done at Mars as well, where we have orbited the moon and done remote sensing of compositions on the lunar surface with technology that simply didn't exist back in the Apollo days. It would have been great if we had had this kind of information prior to Apollo, because what we learned, and again, this is a false color image that gives compositional information. It's not important what the compositions are for this conversation, just that we can now measure stuff like this. If we had known this before we had flown to the moon, we would have recognized that all the places that we ended up landing were really weird. They are geochemically anomalous. They are not the average moon. There's no way we could have known that before, but that's just how it turns out. So even though we have gone 6 times and we have walked around 6 times, we've covered the total area, if you add all that up, is smaller than Manhattan Island. We have only scratched the surface of what the moon can tell us. And we have never been to normal moon yet. Next, please. And there we go. There's the cursor. Okay, skip this, please, in the interest of time. Okay, before you click, Meg, I want to explain what we're about to see. This is another animation. It lasts a couple of minutes, I want to say. And this is, I told you we were going to view the poles of the moon a little bit because they're special areas. And this animation is going to show you why. Now, before we start it, though, I want to point out a couple things. First of all, what you're going to be looking at is all imagery that has been collected by the only orbiter NASA has at the moon right now, called Lunar Reconnaissance Orbiter. It's been up there for a little over 10 years now, and has taken some incredibly high resolution imagery of the lunar surface, revealing a whole new world in details we've never been able to see before. I could talk for 3 hours just about LRO. But one of the things that came out of that was this mosaic we're about to look at. And what we have been able to see is that at the South Pole, okay, hang on, let me take one big step back for just a second. The reason we have seasons on Earth, the reason that we have summer and spring and winter and that all days are not the same length all the time is that Earth is tilted on its axis by 23 degrees. And so in the summertime, our northern hemisphere is pointed, the axis is pointed toward the sun, it's pointed away from the sun in the wintertime. And so the kind of, we've all seen this, the sun stays up less time in the fall, it sets further to the south if you're in the northern hemisphere, all the things we know from having grown up. Well, but the moon is almost straight up and down, just a tiny bit off of straight up and down. And that means there are going to be places at the poles where the sun's just going around the horizon all the time, never gets high and low. It's just always going right around the horizon. And because the moon is so heavily cratered, some of those craters are so deep that because the sun's always coming in sideways, there are bottoms of these craters that never, ever see the sun. Talk about the places where the sun don't shine. This is it. Okay, so what we're going to do when we start this video in just a second, one more second, Meg, is we're going to see the globe of the moon here tip over so that we're going to then come zooming in on the South Pole. And I'm going to stick my finger right on the camera. We're going to come zooming in until we see this one crater that we named Shackleton Crater, which is sitting almost exactly at the South Pole. And what you'll see is we're going to hold our view on the moon and you'll see the sunlight going around us. We're going to fix our frame of reference on the moon and let everything else move around us. You'll see the shadows moving around and you'll see that crater only ever get lit up on the rim. You'll never see light in the middle of that crater. So Meg, with all that long introduction, hit it, please. Oh, no, back up one time, and then you got to actually click that thing to make it animate. Great. There we go. Beautiful. Thank you. Okay, so now you see the sun moving around because we are holding our frame of reference on the moon, and we're zooming in, and now you can kind of see there's Shackleton crater. It's got bright rims, but the inside just stays dead dark the entire time. Okay, cool. That's going to be really important. Now, next, please, Meg. Back one, please. These diagrams, now these are zoomed way in on the South Pole. If you look at the crosshairs, you'll see just off to the right and down a little bit, that's Shackleton crater, the thing we were just zoomed in on. And on the left-hand side, this diagram illustrates, on average, how much illumination any given spot would receive. The maximum is about 50%. About half the time it's day, it's about half the time it's night, normal. And you see that around the edges. But when you look in these craters, you see that it goes all the way down to 0. The sun never shines there. On the right-hand side, this is another one of these psychedelic colored diagrams. This time, the colors refer to temperature. The hot colors are warmer, the cold colors are colder. So what you see is in these same dark, we call these permanently shadowed regions. Pretty obvious why we would call them that. They are always in shadow. And they are so cold. They're the coldest temperatures we have measured anywhere in the solar system. They are colder than the cloud tops of Jupiter. They are colder than the mountains of nitrogen ice on Pluto. It's cold, y'all. It's like 10 degrees above absolute zero, where all molecular motion stops. So it's a really forbidding kind of environment. Next, please. But one thing that means is if there's anything floating around up there volatile, like water or any kind of gas or anything that gets into one of these dark places, it's never going to leave, because it's never going to melt. It's never going to get above its vaporization point. So these permanently shadowed regions are called cold traps. If there were ever any volatiles on the moon, say from an early atmosphere or from volcanic eruptions or from things coming in with comets hitting the moon and ultimately migrating around the surface, if it ends up here, it's never going to leave. And there's a really good chance, in fact, we have made measurements by crashing a spacecraft into one of these places and looking at the plume that it generated. We know that there's water ice in these craters. That's a game changer. That is a real game changer for human exploration. And we're going to talk about that when we get to our last section about Artemis. Next, please. Okay, we're going to take, before we do that though, we're going to take a short detour through some real hardcore science now. Next, please. How does all this tell us how Earth-Moon system came to be? This is an artist's conception of the very early times of our solar system, when our initial ball of gas and dust started to rotate for some reason. There's always some little gravitational disturbance that will get something moving. And once that happens, then it's kind of a runaway effect. And you'll see this cloud will start to self-organize into bigger and bigger clumps. The big clumps get bigger at the expense of the smaller bits, and eventually you're going to get chunks of stuff. This was a conceptual model for many, many years, and only in recent times, the past 10, 15 years, have we developed the capability to look into our galaxy and actually see this process in action. And those images along the bottom of this diagram are deep space images taken by a couple of different space telescopes in different wavelengths, looking at stellar nurseries, places in our galaxy where stars are being born, and they can see this actually happening in real time. Well, I say real time, in however many light years away these things are. So these processes were happening some years before the light got here, of course, all those caveats in there. But this is exciting to see these things really happening. Next. So now we're going to think about what's going on in the very beginning of the solar system's history. And let me paint a picture here for you of what kind of an environment we're looking at. All these chunks are forming. We call this process accretion, A-C-C-R-E-T-I-O-N. These things accrete together. And as that process proceeds, there are going to be big impacts between the big pieces every so often, until, this is going to go on and on and on and on until there are no big pieces left. This is the kind of environment we had in the first tens of millions of years, maybe first 100 million years of solar system history. Now, that sounds like a really long time, and it is. 100 million years is a very long time. But remember that the Earth, the solar system, is 4.7 or so billion years old. So 100 million is just a very small fraction of that whole 4.7 billion. So it's still very early on, still a small segment of history. What I'm going to show you in the next thing is another animation that illustrates a huge impact that our own Earth experienced. And we know this because of what we've learned from analyzing the lunar samples. And I'll get into that in just a second. At the time that this happened, the whole accretion process had been going on for some tens of millions of years, to the point where there were some pretty big pieces out there. And one of those that we now estimate to have been about the size that Mars is today, which is about 1/3 the size of our Earth, came and rammed into the very, very early Earth. And we call, we're not very imaginative, we call this thing the giant impact. And we think that it is this process which formed the moon from pieces of both our Earth and the thing that came in and did the impact. So what you're going to see in the next animation is the right-hand side of this thing animated. This is a numerical model, a calculated model. The colors, again, refer to temperature. So the hottest colors are hot enough to be molten. And I want to focus on this for just a second before we run the animation. When I say molten, I mean liquid, melted rock. Have you seen some of the pictures of volcanoes recently? There's volcanoes going off all over the place right now. Iceland is erupting. Hawaii is erupting. There's an island in the middle of the Indian Ocean. There's one in the Caribbean. When there's a volcano bubbling, that's molten rock, liquid rock. All right, let's run it. And what I want you to focus on is just how much of the Earth goes to that red color. Oh, skip this. This is math. We don't want math. Okay, go ahead and run this. So the impactor, got to go to the beginning. Got to start at the beginning, please. Whoop, there we go. All right, great. There's the impactor. It hits the Earth. Notice right away, the entire Earth goes red. These bits and pieces go flying around. They form what's kind of like a ring around Earth, like Saturn has a ring. But notice, the entire Earth is molten rock. No mountains, no continents, no oceans, just ball of magma. Now, eventually, this process stops, and all this stuff you see around the margins will coalesce and form the moon. Next, please. We're going to see another animation, so make sure go to the beginning and then hit the start if you would. We're going to see the very same process now, but this time in a cartoon animation. This is made by the BBC. Go ahead, please. So here comes the impactor, and it's a bad day on Earth. It's going to hit the Earth, and we saw the numerical calculation, but this is a really good image of what it might have looked like. And there you see the entire impactor is completely vaporized. Earth itself is split apart, melted, and now you can see all the stuff flying around Earth is starting to coalesce and form our moon. And it too is 100% molten. And we learned that it was molten first, and that's what gave us the idea for this whole story. Now here's a picture. This is what it might look like. Now you're on Earth, you're in a magma ocean, and the moon is much, much closer to Earth than it is now. And it's rising very quickly. It probably takes only about 4.5 or 5 hours to get all the way across the sky at this time. So this is what the Earth-Moon system looks like about 75 million years after the beginning of time. It's a very different place from how we are now. Okay, we're going to do one more animation. We're going to pick up this story now with the moon being completely liquid. Go ahead, Meg, and you can start this, and I'll go to the next one instead of repeating. Great, and start at the beginning. You have this down cold now. Okay, now we're looking at just the moon. We're picking up right where we left off. So here we are about 4.5 billion years ago. There's our molten moon, and it's cooling off, forming a crust. And this is just the normal thing. And then the bombardment history starts. Remember I talked about accretion? There's still big pieces out there floating around, and they're still coming in and raining down on the inner solar system. The first one makes that giant basin I mentioned a while ago, South Pole Aitken Basin, biggest in the solar system, and we think the oldest on the moon. Almost split the planet in two. And then comes another wave, some hundreds of millions of years later, of heavy bombardment. Accretion is now really winding up for good. All the pieces big enough to make giant craters are getting vacuumed up by all the planets. And so this is what's making the huge basins we see on the lunar near side. And then with more time, it didn't happen right after the impacts. It took a couple 100 million years, but eventually the mantle of the moon melted and that magma rose up and filled in these basins. So when we look at the moon in the night sky today, we see the dark pieces, that's the cooled off lava, and we see the white stuff, which is the initial primordial crust that cooled from the magma ocean. And so now the moon is starting to look a lot more familiar, and we're now in the sort of second half of lunar history. There's still a lot of craters being formed, but they're nowhere near the sizes of these giant ones in the early going. Things are just kind of winding down now. And then by the time we get to, like, I don't know, about 1 billion years ago or so, there's just a few left. And we can still see them, very readily on the lunar surface. And now the moon is starting to look really familiar, like what we see when we look up in the sky, because not much has happened at the moon over the past 1 billion years or so. And here we are today. Okay, next, please. All right, I'm really glad those all worked. I think that's our last animation for the presentation. Okay, now, why did all this stuff come raining down on the inner solar system during those several times? Why is that? Well, what we know now is that I warned you early on that I wasn't going to talk much about the outer planets made of gas. This is the one time I'm going to talk about them. What we have been able to work out is it's very likely that the gas giant planets were in some different position way back then. But then for some reason, they changed their positions relative to one another. And that changed the whole gravity budgets for the outer solar system. And that kicked loose a whole bunch of stuff from the asteroid belt and from the belt of comets that are further out, and threw those things down into the inner solar system, where they created the bombardment history I just got through showing you. All right, let's go to one more slide, because there's a big punchline for all this. All right, that's the perfect spot. This is the big punchline. Now, I just got through showing you that in the first 100 million years or so of the history of our planet, our entire planet was a ball of molten rock. Now, I don't know about you, but for me, that's got to be one of the top 3 most important things that has ever happened to the Earth, that it was once completely melted. But now, the only way we know that is we went to the moon and we picked up the moon rocks and we figured out that the moon must have been molten at some point. Well, how did that happen? And through a long process of trial and error, and I won't go into all the details, we came up with this model of the giant impact, and it seems to hold up really well. It seems to explain everything we can observe to pretty good order. So why did we have to go to the moon to learn this? Because when when Earth was completely molten, there's no rocks. Everything is melted. That is wiping the slate clean. That's like erasing the chalkboard of history. For geologists like me, rocks are the pages in the history book of the story of our world. And all of the pages from the first chapter of our history are gone. They've been ripped. They're not there. There are no pages for us to go look at. The oldest rocks on Earth are some 500 million years after all of this took place. There's no way we could have ever known this unless we had gone to another world, unless we had gone to our nearest neighbor, brought home some of those rocks and studied them here on Earth. It's one of the answers I always give when people say, why do we bother? Why do we bother going to space? This is why. To learn where we came from, to learn important things, not just about the other worlds, but from our own world. Next, please. And I believe this is our segue into the last. Yes, the moon is now the foundation of planetary science. Everything we know about all the world, we start with the moon. Next, please. And I believe we are now moving into the final home stretch. Yes, we are. The Artemis program. Next, please. This is going to go a little faster than the rest. Artemis now, Apollo was the sun god in Greek mythology. His sister was named Artemis. Our plan is to land the first woman and the next man, but also the first person of color on the lunar surface in Artemis. Artemis is different from Apollo in many, many ways. Back in the 60s, it was NASA's game. We were competing against the Soviet Union. There was no commercial space sector. There were no other spacefaring nations to speak of. I mean, there was a very different atmosphere, if you like. In the time since, things have changed a whole lot. Artemis is all about partnerships and coalitions. There is now this really robust commercial space sector. If you've ever watched one of the SpaceX launches where they get something into orbit and they bring those boosters and land them right back down on the launch pad, there's some really cool stuff happening out there. We have international space agencies, Japan, the European Space Agency, the Russian Space Agency, India, Israel is getting into the game. There is a very, very vibrant international partnership of spacefaring agencies. So the return to the moon is going to be different than it was in Apollo, when we just went for at most a few days and then came home. This is a return to the moon to stay. This is our first step of making humanity a multi-world species. I personally believe this to be really important for our future. Next, please. Okay, here's a little artist rendition of what our surface of the moon might look like once Artemis is going. We're gonna build habitats. We're gonna have rovers and bases and be studying all kinds of things. And I remember I was talking a bit about the lunar poles. Next, please. The permanently shadowed regions, and there's water in there, and why that's so important. A reason why that's one of the big reasons why that's so important is that, most people may not know this, but most of the stuff that we use as rocket fuel is really just water. We break up water into hydrogen and oxygen, and it turns out when you recombine hydrogen and oxygen to make water, it's a very energetic process. You get a lot of energy back. And so if there's water ice up there and we can somehow extract it and purify it and convert it into rocket fuel, that makes the moon that's a total game changer about making the moon a real outpost from which we can jump off into further destinations into deep space. Because every kilogram of mass you launch off of a planetary surface costs money, and the stronger the gravity of that object, the greater the gravitational pull, the more effort you got to get something off the surface. Launching from the gravity well, as we call it, of the moon costs you a lot less energy than it does launching from the gravity well of our Earth. This is just a rundown of some of the commercial partners NASA is working with in Artemis. Next, please. We are working with a whole bunch of different partners. And just the other day, NASA selected the SpaceX model on the right-hand side of this diagram to be the vendor that will build the human landing system that will be the ride for astronauts from lunar orbit down to the lunar surface for Artemis mission, for crewed Artemis missions. And that's just last Friday that selection was made. Next, please. Okay, so these diagrams now, we're in the home stretch, just a few more charts left to go. We call these things swoosh diagrams for reasons you can probably guess. These are very schematic, okay? They're meant to just be kind of cartoons of showing the sort of big picture structure of what we're trying to do. We call this an architecture. And so our early missions in the Artemis program will be concentrated on testing out the spacecraft, both first without crew and then later with crew. And during those first years, in fact, starting just later this year, there will be missions launched in what we call our commercial lunar payload services program. These are all robotic, to put measurement devices and landers and rovers down on various locations around the lunar surface to start to learn things that we haven't been, using techniques that didn't exist before about the lunar surface that help us plan just where we want to land and how we want to work when we get there. Next, please. Ultimately, what we intend to do is put humans down, again, not just a couple at a time, but build up the capability for maybe month, 2 month, 3 month long stays on the lunar surface in a habitat, maybe in a moon base. We're going to try to learn to live off the land as best we can, convert lunar soil into usable things like oxygen and water, both for fuel and for drinking and growing plants and so forth. And when we have spent this time really getting our space legs, really getting our feet under us for how we live and work on another world, that's going to teach us what we need to know to then go on to Mars and other destinations. Next, please. Now, this is now really long term, of course. And what I want to say is, though these 3 diagrams I just showed you, these are being updated on a weekly basis, okay? Because as you might imagine, there's a lot of moving parts here, and there's a lot of ways that this part of the plan can affect that part of the plan. So I don't want you to hold me to anything that's on these. A lot of these things can change and so forth. And you'll notice there's no years on here, because we know that, you know, we're going to have to do this safely, for one thing. You know, we have an ambitious timeline to get humans to the surface, but we also know we have to do it safely, and we're not going to compromise on the safety of our astronauts. Next, please. And this is almost my final slide now. This is, again, I said this before, but this is the plan by which we sustain a human presence on the lunar surface, to become an off-world species, to become a species that can spread out through the solar system. You know, again, I was born in 1960. I grew up on Star Trek. Okay, I want the United Federation of Planets. You know, I want there to be this something that you know, all of us as humans can buy into, and because what we're doing really is for the benefit of everyone. And I'm going to close with those thoughts with our next slide. I'm pretty sure. Yes. So here we go. Our whole program now here at NASA, you know, we're building on our past accomplishments, but we're looking to the future. We are making use of everything we have learned about Mars and the Moon, from samples, from remotely sensed data, from all of our navigation stuff. We are building partnerships and coalitions with international agencies, with our commercial sector. There's government, academia, and we're in this for the long haul. This is a return to the Moon for us to stay, and this is the message I always want to leave everyone with. You know, when we talk about space flight and space exploration, naturally, there's a lot of focus on the astronauts and the engineers and the scientists and so forth, and that's fine. But for every human that has flown in space, it has taken at least 10,000 people on Earth, maybe 20,000 people on Earth, to do a huge range of things to make that possible. And, you know, to their everlasting credit, every single astronaut, that's the first thing they say is, if it weren't for this amazing team of people, I wouldn't be at the top of this pyramid. I wouldn't be the lucky person to go into space. And we need everybody. We need architects. We need people who build roads. We need people who drive trucks. We need lawyers and accountants, and every walk of life, wherever your road is in life, at whatever point in that road you're on. Because, you know, if you're like me, there's more in the rearview mirror than there is out the windshield. There is going to be a place when your road and our road is the same road, and we want you to come along. You know, the young people today, they are the Artemis generation, in the same way that I come from the Apollo generation, and we are actively passing that torch to these next generations to take the lead, so that, you know, they can take us to these next giant leaps. And here we are at the end of, well, it's not the end yet, but we hope we are coming close to the end of this terrible pandemic and all of the other disruptions that our society has endured for this past year plus, from the disease situation to the economic turmoil, racial injustice and violence, and so many other terrible things. And what we at NASA firmly believe is that it's our responsibility to help any way we can, to inspire us all to move into the next thing. And we know that in the post-COVID world, and Meg and I were talking about this, and Jennifer in the beginning, the world's going to be different. We're never going back to exactly how it was, never. And we have an opportunity. You know, I'm sure there are some people listening to me now who are old enough to remember the post-World War II years. You know, I'm very blessed that I was born of parents. I was the youngest of 5 kids, and I got to know my parents really well. They were born in 1919 and 1922. And so I got to live through their experiences in a lot of ways. We have an opportunity, those of us alive now, to rebuild our society after COVID and after all of its attendant turmoil. That's an opportunity very few generations get. Artemis and the things that NASA are doing is a way we want to help make that new world for all of us. And I'm really looking forward. I'm very excited about what our future is going to bring, and I'm looking forward to sharing it with all of us here on Earth and in our country. thank you for your attention today, and I'm looking forward to answering as many of your questions as I can. Boy, there's a lot of them.
Wow, David, thank you so very much. Would you like us to read off some of the Q&A, or do you want to just peruse it and answer as you go?
You know what? I think it'd probably be cleaner if someone moderates for me and picks a question and asks me, because
Okay,
otherwise
well,
I'll fumble.
To conglomerate a couple for you, because they're asking about the atmosphere on Mars and the ability of the atmosphere to support the helicopter. So the first question is, what is it the atmosphere made up of? And is there, how is there enough to support helicopter flight?
Great questions, great questions. Two things, so I'll get the composition first and then talk about the density. Composition of the Martian atmosphere is dominantly carbon dioxide. There's a little bit of nitrogen and oxygen, but it's CO2 and some methane, and there's some argon, about 1% worth of noble gas argon. Very, very different from the Earth's atmosphere. It's incredibly thin. The atmospheric pressure, at ground level around the equator at Mars is about 1/1000th what it is on Earth. For all intents and purposes, it's a vacuum. You could not survive without a spacesuit. Excuse me. And yeah, as the question said, it's really thin. How can you fly? Excuse me, something like that. The atmosphere where Jenny is flying is about the same density as atmosphere on Earth at an altitude about 3 times as high as Mount Everest. On Earth, we've never flown a rotorcraft that high. And it takes specialized aircraft, fixed wing aircraft, to get to those altitudes. So to do that on another world, it's pretty impressive. And basically what they had to do was build chambers. All this development work was done at the Jet Propulsion Laboratory in the LA area in California. And they were able to build a chamber and pump in the gas of the right composition and the right density at the right temperature, and just test and go back to the drawing board until it would work. And this took really incredible engineering skills, and it also took some important developments in material science, in developing materials that were lightweight but still strong, that could withstand high temperature extremes. So this has taken, it took, where are we? It's 2020. It's pretty close to a 10-year development cycle to get that thing into shape. So yeah, it was not a simple matter, but they did it.
And one more question on the helicopter. Would it be able to right itself if it flips over?
I think not. I definitely think not, because it's designed for when the rotors turn, for the thrust to go one direction. So if it's upside down and if it could even turn the rotors, which I doubt that it could if it were on the dirt, it would only be pushing itself into the dirt further. So yeah, that would be a bad day if that were to happen. But again, it's a tech demo. Whatever happens is fun. We're going to learn stuff. That first flight, it was absolutely perfect. It was exactly what the engineers had designed it to do. And in fact, that's what's been going on with this whole mission. There was the only thing that didn't work on the way down. There was a microphone that was built into the lander, and it didn't turn on during the landing sequence. They got it turned on once it landed, and we've actually, recorded some sounds on the surface of Mars, but it didn't happen while it was coming in, which would have been really cool to hear. But that's it. Everything else worked almost perfectly. It's one of the best performing missions NASA's ever flown.
And you have many questions on international cooperation and how well do we work with others, and are we expanding to work with other countries, and also business partners? Okay,
great, excellent questions. Yes, we have the thing that the model, I think, that has really led the way in establishing and maintaining our relationships with our international partners is the International Space Station, where we are partners with Russia and Japan primarily, but also the European Space Agency. And so this has been a way with, a lot of multi-government bureaucracy had to happen to make all those things go. And we have learned how to work together and how to design together. And so there is a really good foundation that has been built up over the past couple of decades. Now, on the non-human spaceflight side, on the robotic exploration side, NASA has also been collaborating very successfully with the Japanese Space Agency, JAXA, with the European Space Agency as well, on missions that have flown to the Sun, Mercury, Venus, the Moon, Mars, and the outer. I mean, it covers the entire waterfront. We have our scientists work really well together. We are fortunate that there is a really good collaborative, collegial atmosphere. Of course, there's competition as well, but it's healthy and it's good-natured. And so, one of the joys of my career is having had the opportunity to work with some of these international partners. It's a real privilege. Now, on the business side, again, this has all happened, in pretty recent years. 15 years ago, the notion of a commercial space sector, especially for anything outside Earth orbit, just didn't seem realistic, but that's no longer the case. There are now real business plans that can be written for doing business in Earth orbit and even into the region of space surrounding the moon. As we go forward with Artemis and our commercial lunar payload services programs, we anticipate that there will be multiple opportunities for lots of companies to be able to basically sell a ride for a payload, a scientific payload, to a research group. If you can come up and if you can figure out how to build the instrument and stick it on our lander, we'll charge you some X amount to fly it and land it where you want it to be landed. So that's another game changer. So all of these things are new paradigms, if you like, for how we go about space exploration, and they're all really positive developments. So it's a really exciting time.
Okay, here's scientists monitor asteroids for danger to Earth, but shouldn't we also be concerned about the ones that hit the moon and cause it to affect our world significantly?
The good news there is that, first of all, that there are very, very few large chunks still out there. There are some, and we don't know exactly where they are. But that's the first thing, is that the likelihood of, like a civilization threatening impact to happen, very, very low. Not zero, though, so we do need to be diligent. Now, the also good news is an impact that hits the moon is very unlikely to have any effect on Earth, unless it were big enough to send so much debris out that those things that could then come and hit our world. The likelihood of that happening, again, is extremely low. It's not zero, but it's extremely low. We don't spend a lot of time, frankly, concerned about an impact on the moon hitting Earth. But we do have at NASA a whole, what we call a planetary defense line, where we actively look to catalog the near-Earth objects that could in one day intersect our orbit. And, so that we could prepare if a bad day is coming. Right now, to our best of our knowledge, there is no planet killer out there that's on its way to hit us. There are a couple of large objects that we know are out there and whose orbits do cross Earth's orbit, but every time they do, Earth's on the other side, so it's not like they happen at the same time. There is one object out there you may have heard about in the news. I can't remember the exact name. It might be Apophis. Don't quote me on that. But that it's one that was thought maybe it could hit Earth in about 2200 or something like that. The most recent trajectory calculations on that, because it comes into sight every so often and we can observe it and refine our understanding of its path. It doesn't look like it's got any chance of hitting us for many hundreds of years. So that's where we are right now. However, if something comes from someplace we don't expect, if something comes at Earth, let's say from right out of the sun, if the sun's behind it, we can't see it. There was a meteor that came in above Russia on Valentine's Day. I want to say it was about 2004, 2005, a little town called Chelyabinsk. And this thing came in and exploded over the city. It was several miles high when it did. But that was a pretty big chunk. That was a couple of meters across. And the energy released by that explosion was equivalent to about 3 times the size of the nuclear weapon that was dropped on Hiroshima at the end of World War II. If that had exploded, a whole lot lower, it would have been really bad. However, and the reason I bring that up is because it came out of the sun. It was, we have telescopes and things pointing in every which way, but we can't look into the sun, and if something comes from that direction, we're not going to see it until it's on top of us. And that's what happened with Chelyabinsk. So it's a good thing it was small. And it's a good thing it was over a relatively unpopulated area. But if that same sample, with that same chunk of stuff, had come in 3 miles, 4 miles lower and over a big city, there would have been a lot of people died. It would have been a destructive, terrible event. So planetary defense is a real thing, and NASA has something like quadrupled its investment over the past 5 years in this because, you know, we recognize this is something we need to be looking out for. Good questions.
Okay. We have questions asking for, is there a realistic timeline for going to Mars? And where do you think humans go beyond Mars? And are we going to be able to reuse some of the things we've landed on other planets like Mars and the Moon?
Yeah, boy, I love these questions. I can't say a year for when we're going to get to Mars. It won't be this decade. May not be next decade. The key thing is we have to learn what we're doing, and we can't prejudge how long that's going to take. We have to just do it until we figure out, all right, we think we know enough, and then we can go on to that next step. You know, when you go to the Moon, you're only a few days away. You can launch anytime, almost any day, and get there. You can launch from the Moon almost any time and come back. You may have to wait a little bit till things turn, you know, to just the right. But you're never going to have to wait more than a day or so before you can make a launch. Not so when you're going to Mars. Literally, the planets have to align properly before you launch from one object, from one of those planets to the other. It takes a minimum of 6 months to get there under the most favorable conditions with your pedal to the metal the entire way. And then you got to wait about 18 months before you can even think about coming back once you've landed, because again, you have to wait until the orbits line up so that when you launch, you can catch up with Earth. You can't just launch any old time. So it's a high risk proposition going to Mars. You better know what you're doing before you go out and take that kind of a risk, because you're on your own. The other thing is that, you know, even though the Moon is only 250,000 miles away, it takes almost a second and a half for a radio signal to get there and back. So that's even worse when you go to Mars, which is tens of millions of miles away. It takes many minutes for that to happen. Sometimes 10, maybe 15 minutes for the radio signal to reach the planet. So the way we operate on Mars will be very different. The astronauts will not be just constantly having the mission control in their ear, because the time lag will be too much. So it'll be much more autonomous. They'll be making their own decisions. That's we have not operated that way before. We have to learn how to do that. So my answer is it's going to take as long as it takes for us to figure out how to do it right and do it safely.
Okay.
Oh, and then more questions. And where are we going from there? Other places I think that are very likely objects for human exploration include some of the larger asteroids in the main asteroid belt, like Ceres and Vesta. These are objects that are, you know, they're big. I mean, they have plenty of gravity. We could orbit there. We could put people down. That would be a stretch goal for you know, Mars. Maybe the satellites of Mars. Mars has a couple of small moons of its own. But that's probably the next place after Mars would probably be some of the larger asteroids. And I think I covered those questions there.
And will Mars be a one-way trip, or is it going to be a round trip, or how are people going to come back?
Yeah, that is absolutely the plan, for it to be a round trip. Yes. Now I'm sure you've heard some of the same things in the news, that there are, you know, sort of private efforts being considered where it would be a one-way trip, and but that's not NASA's thing. That's somebody else's game entirely. But we are all about bringing them home. We're not about making one-way trips.
Okay. They're talking about meteorites found on Earth that came from Mars, and how were they affected by leaving the Mars atmosphere and traveling through space?
Yes.
And passing through Earth's atmosphere.
Yep. And I promised to tell you how we know that they came from Mars, and the atmosphere is the answer. So this is a good one. Okay, let me start with the second one. You know, we got these meteorites. How do we know they're from Mars? And it does have to do with the atmosphere. I mentioned the Viking landers when I was telling you about the history of Martian exploration. Those two landers measured the composition of the Martian atmosphere with instruments they had on board, both in terms of what elements are present, but also something we call their isotopic composition. And that's kind of a geochemical fingerprint. We can think about it that way. Now, we had a set of meteorites already by then that we had been studying for about 20 years. The first ones, I think, were recognized in the early 60s. And we knew that they were unusual. We knew they were different from a whole bunch of the other meteorites because of their geochemical fingerprints, which demonstrated that they had to come from a fairly large body. in order for the geochemical processes that we could observe to take place. Those things just don't happen on small asteroids. They just don't. You have to have something big enough so that gravity can get things moving inside the world, okay? And so we could see the signal in these meteorites that, okay, it had to have come from an object at least, the size of Mars. So that there was circumstantial evidence for it, and people were thinking by process of elimination, Mars is probably the best candidate for that. But once the measurements that Viking had came back to Earth, a couple of scientists, and in fact, these were people I got to work with at NASA Johnson. I was their boss when I came there. It's just crazy. Had the brilliant idea to measure a little blob of stuff in one of these meteorites that was made of, sounds like something normal, glass. But it's not just any glass. Remember I talked about molten rock, liquid magma. If you reduce the temperature of that stuff really quickly, you can do what we call quenching it, and it will not have enough time to form crystals in a rock. It'll just quench to a glass of the composition that the magma was. And when that does that, this glassy stuff, you can put a lot of atmospheric gases into that stuff. Very, very easy to measure quantities. And so my friend, Don Bogart is his name, had the brilliant idea to measure this glassy stuff in the meteorite for the kinds of things that we knew to be in the Martian atmosphere. And it is a smoking gun, 1-to-1 slam dunk match. Now, I'm here to tell you, in the science game, the way we go about our day-to-day business is doing everything we can to prove our ideas to be wrong, okay? We say, this is a hypothesis. Let's tear it down. Let's throw everything we can at it. If it survives all that, that's a working hypothesis. We might be able to take that to the next level. To actually prove something is something we almost never get a chance to do. We come up with a story. It's kind of the old Sherlock Holmes thing. When you eliminate the impossible, whatever remains, however improbable, must be the truth. That's how most science is done. But this is a case where we were able to have absolute smoking gun evidence, proof that these things came from Mars. There's no way you could get a match that close in this sample any other way. And once we did that first measurement, we went to a whole bunch of others that we had from this collection and realized, hey, almost all of them have this. They're exactly the same. So now we know that this set, at that time, I think there were about 15 of them. They're now almost 70. We now have the diagnostic tool to be able to determine, is this from Mars or not? We can make that measurement. Oh, there's your answer. That's a Martian meteorite. Open and shut. The Mars atmosphere is the thing that helped us do this. And I'm trying to remember now what the other part of the question was to do with the atmosphere. Help me out.
Did leaving Mars and traveling through our atmosphere affect the rocks?
Yeah. Absolutely. Sorry. Yeah, it absolutely did. The atmosphere of Mars on the way out, when it was blasted off the surface, because some impact came down and flung that thing off the surface with enough velocity to get into space. That's how it got off the planet. That part of that trip through the atmosphere probably had almost no effect because, again, the Martian atmosphere is very, very thin. But when it comes into Earth's atmosphere, way thicker, if you go out on a dark night and you see little, meteor trails, that's what that is. Most of the things you see are very tiny. They're like the grain of sand that make those little streaks. The things that are about the size of your fist will make one that goes, maybe you can actually see it hang there for a second or so after it goes. So when a piece of material comes into Earth's atmosphere that way, the outer skin of the rock will melt. And we've been talking about melted rocks all day here. When it does that, and this is something that is very counterintuitive. And I didn't, I'm a geologist and I didn't know this when I first got into the planetary game, that even though it's actually molten on the outside and it's making a red hot trail through the sky, the inside stays deeply cold. We use this exact same principle to bring astronauts home through the atmosphere and reentry. We build a layer on the stubby nose of that capsule that is intended to melt as it comes through Earth's atmosphere and heats up because of the friction. The thermodynamics of the situation dictates that the process of melting sucks up so much heat that all of that heat never makes it inside the capsule. The fact that all these astronauts have come home safe proves that that's how it works. Same thing happens for a meteorite coming in through Earth's atmosphere. The outer skin melts completely, but the inside stays as cold as the depths of space. And so if you can actually find a meteorite, you watch it come down and you can go get that rock, keep it cold as best you can. First of all, don't touch it with your hands. It won't hurt you, but you can compromise the sample. Get some aluminum foil and some baggies. And if you can, dry ice. Get that stuff in foil, stick it in a Ziploc, close it up, put it in an ice chest, and throw some dry ice on there and call the Smithsonian, and you'll be a hero.
And I think the question we're going to end with, it's come up a lot of times, is the Artemis Moon Project going to be a U.S. project, or is it a World Earth project?
It is a World Earth project, absolutely. This is NASA's program is called Artemis, but it is baked in that we have partnerships. In fact, we have the European Space Agency is building one of the main components of the whole system. Absolutely intended to be something that is for all humanity, because we recognize that the world is not the same as it was back in the 60s. Cooperation and collaboration is the future. Look at the things NASA has been able to accomplish during the years of the pandemic. It really shows what happens when people, put their heads together and tackle a problem together. There's not much we can't do. And so, it is absolutely meant to be something that we all go along with, whether you are actually part of the program, or whether you're just here rooting for us at home. We're doing it for everybody.
And the other big question is, can they email you with follow-up questions?
I'll tell you what you can do is, if you would, Meg, and Jennifer, please capture the chat box.
I can do
there's
that.
A ton of questions in there that we didn't get to. And what I'll do, you can email me that list. I'll take some time over the next week or two. It won't be the next day or two, I'm afraid, and I'll answer all of them in writing and send that back to you, and you can share with the group. Would that be okay?
That would be wonderful.
I'm happy to do that, because I can see a whole bunch of questions here that I could spend hours talking about. And I don't know if you've noticed, but I kind of like what I do. I really enjoy this. And so it is a big part of my job to do this, but I love being able to communicate the exciting things we're doing and to help you learn. So I will take the time to answer all those questions. So throw some questions in the chat and I'll get to them.
Thank you so much for your generosity in offering to answer those questions. And we will definitely relay that back to the attendees through AARP and also through Ollie. Thank you so much, Dr. Draper. David, you've been so awesome. We learned so much, and your enthusiasm came across for the passion that you have, obviously, for this exploration of learning. And really what you're doing is helping humanity and making the world a better place. And we thank you so much for participating in this program with us today.
It's been my privilege and my pleasure. And I want to thank you all for your kind attention and for the invitation to come and talk to you today, and for the support that we get here in the country for what we're doing with NASA. Every time we talk, we hear it, we feel it, and we appreciate it. Thank you very much.